Right. Now, from what we have seen, we have the arterial end, the venous end. We also have that part midway. Now, at the arterial end of the capillary, remember we are talking of two forces, the hydrostatic pressure and the osmotic pressure. Hydrostatic pressure and osmotic pressure. Now, at the arterial end, that is the end near the arterial, the hydrostatic pressure is greater, higher than the osmotic pressure. Why? Because at the arterial end, there is still that high force, there is still that great force due to the contraction of the artery, of the heart. There is that pumping action from the heart. So the hydrostatic pressure is high at the arterial end, much higher than the osmotic pressure. What does that mean? Now, because of the higher hydrostatic pressure, small molecules like some white blood cells, ions, antibodies, hormones, fatty acids, like we've mentioned them, are forced out of the blood within the capillary, across the capillary walls, into the tissues, forming tissue fluid. When we look at that image, at the arterial end of the capillary, the hydrostatic pressure is higher than the osmotic pressure. Now, that high force or that high hydrostatic pressure forces molecules that are small, like we've mentioned them, out of blood, across capillary walls, go to the tissues. Therefore, those molecules now enter the tissues, surround the cells, forming what we are calling tissue fluid. But what follows? As the blood continues to move within the capillaries, now from arterial towards the venous end, as it continues to move, due to removal of those molecules, what happens to the hydrostatic pressure? It lowers, it decreases. Meaning, as blood flows through the capillaries, from the arterial end to the venous end, the hydrostatic pressure decreases because molecules move out of the blood in the capillaries into the tissue fluid. But midway the capillary, the hydrostatic pressure is equal to the osmotic pressure. Because they are equal, this now means that materials cannot move out of blood due to a high hydrostatic pressure. Why? Because it is now equal to osmotic pressure. They balance themselves. So at that point, midway the capillary, where the two forces balance each other, materials move from blood in the capillaries by diffusion. So these materials like glucose, hormones, the antibodies and the others, now simply move along a concentration gradient. Equally, remember in the tissue fluid, there is carbon dioxide and other wastes. Because in the middle of the capillary, no effect of hydrostatic pressure, no effect of osmotic pressure, it is only diffusion. Carbon dioxide and other wastes, which are in a high concentration in the tissue fluid, equally diffuse from the tissue fluid across the capillary walls into the blood. Where? Within the capillaries. So in the middle of the capillaries, due to osmotic pressure balancing with hydrostatic pressure, materials diffuse from blood into the tissues or into the tissue fluid, while the wastes and like carbon dioxide diffuse from the tissue fluid back to the blood. At that point we said no net movement of water occurs. That is in the middle of the capillary. But how about at the venule end? At the venule end, remember that as the blood moves from arterial towards venous, what happens to the hydrostatic pressure? It decreases. Therefore, at the venule end, hydrostatic pressure is much lower than osmotic pressure. Hydrostatic pressure is much lower than osmotic pressure. In other words, osmotic pressure is higher than hydrostatic pressure. But remember, osmotic pressure is due to the proteins in blood, and that force tends to pull water molecules back to the blood in the capillaries. Now, because osmotic pressure is higher at the venous end, this means that water molecules are pulled from the tissue fluid back to the blood into the capillaries. This causes water molecules to move from tissue fluid back to the blood within the capillaries by the process called osmosis. By osmosis. In so doing, it means the tissue fluid, some tissue fluid is drained back to the blood. That is why we say that some tissue fluid, after being formed, is drained back to the blood within the capillaries, but at the venous end. Why? Because at the venous end, osmotic pressure is higher than hydrostatic pressure. This causes water molecules to be drawn back, hence tissue fluid being drawn back into the blood. However, overall, the amount of materials that move from blood to the tissue is far much higher than the amount of materials that move from the tissue back to the blood. Meaning, most of the materials remain within the tissue, hence forming that fluid which we are calling tissue fluid. Therefore, in summary, if you're talking about formation of tissue fluid, you need to show us that it is formed by ultrafiltration. However, involving processes like hydrostatic pressure or forces like hydrostatic pressure and osmotic pressure. Tell us at the arterial end, hydrostatic pressure is higher than osmotic pressure. Therefore, it forces materials, those materials we've mentioned, the oxygen, glucose, amino acids, to move from blood across capillary walls into the tissues, forming tissue fluid. In the middle of the capillary or midway the capillary, osmotic pressure is equal to hydrostatic pressure. Therefore, molecules now move by diffusion. Well, this means that some wastes diffuse from tissue fluid to the blood, while at the venous end, osmotic pressure is far much higher than hydrostatic pressure, causing water to be drawn back into the capillaries, in so doing draining some tissue fluid back to the capillaries. However, the tissues are not only connected to capillaries, which are connected to venules and arterioles. Look at that image. On the right hand side, we are seeing lymph vessel. Lymph vessel. Lymph vessels have swellings along them known as the lymph glands or lymph nodes. Therefore, the lymph vessels and lymph nodes collectively form what we call the lymphatic system. Meaning the lymphatic system is made of lymph vessels, the lymph nodes, and a fluid flowing within them known as lymph. Those three are the components of the lymphatic system. Now, when we look at that visual, we have seen that some tissue fluid is drawn back into capillaries by osmosis due to a higher osmotic pressure than hydrostatic pressure at the venule end. But some excess tissue fluid is drained into the lymph vessel. Hope we are seeing that arrow. That arrow showing us the excess tissue fluid drained into the lymph vessel. That means when the tissue fluid enters the lymph vessel, It is no longer called tissue fluid, but it is now called lymph, leading to formation of lymph. What happens to that lymph after entering into the lymphatic system? The lymph flows within vessels. It flows within vessels in the lymphatic system, where a type of white blood cells called phagocytes, do you remember the phagocytes? Called phagocytes, from the lymph nodes, remove the bacteria, any bacteria and any foreign particles. Meaning what remains is lymph without bacteria, without foreign particles. It then gets drained to blood, meaning lymph joins blood. It joins the blood circulatory system at a point where we have the subclavian veins. Subclavian veins drain blood from the limbs, the four limbs. They drain blood from the four limbs. Therefore, lymph joins the blood circulatory system at a point where they join with blood from the subclavian veins, therefore leading to formation of lymph. So that brings us to today's session, where we have seen the properties of the homeostatic system. We've also seen what tissue fluid is and how tissue fluid is formed. Till we meet again next time, we shall continue from that very point. Keep safe. COVID is real. We need you alive. Please observe the SOPs. Put on your masks. Wash your hands. Sanitize. We need you alive. Together, collectively, we can fight and defeat COVID. Bye-bye.